exploring the vast ocean, climate science explained, and a wonderful scientific adventure, all in this episode of Goggles Off. Welcome, everybody, to another episode of Goggles Off, the show where we get outside of the lab to talk to scientists about their lives and their research. Today, it's my immense pleasure to welcome my next guest, Paige Hoel. Paige, how are you today?
I'm doing great. How are you doing, Brandon?
I'm doing super good. It's a delight to have you on the show. I first kind of became aware of your scientific journey in your newsletters, your weekly newsletters that you would give out, kind of detailing your experience on the research vessel,
Mm-hmm.
the Thomas Thompson. But
Uh-huh.
before we kind of describe that story, I actually kind of want to give the audience a little background about you. So you're currently a PhD student in oceanography at the University of California at Los Angeles.
Yes, sir.
And before that, you completed not one, but two bachelors in science, one in earth science with an emphasis on climate, and then the
Mm-hmm.
other in physical geography.
Yep. Yep.
hmm And then a whole list of publications and presentations, and then these fantastic newsletters to detail your wonderful scientific experiences. So lots of accomplishments for you. Um,
Thank you for the introduction.
of course. But to touch on, the research vessel, the Thomas Thompson experience that you had, I just want to kind of give the audience a little background on that. So that was with the organization Go Ship, right? So that stands for
Yep.
uh, the Global Ocean Ship-Based Hydrographic Investigations Program.
Yeah.
I
Yeah.
looked at my notepad, but I did not have the note on hand, so I had it off memory that. Um,
Yeah.
And so, can you tell me a little bit about, the goals of uh, the research expedition, and what it was all about, what your experience on the Thomas Thompson set out to do?
Yeah. Yeah, of course. Yeah, well, thank you for the introduction. So, yeah, I am currently in the second year of my PhD at UCLA as an oceanographer. And in oceanography, we have to collect measurements either like manually in the water or through like models and in assumptions. But the traditional way and the way that we've pretty much always done it is collecting our measurements in the water, which makes perfect sense, right? But the problem is that the ocean is really big and it's really deep. And so, um, as we began to like get more into oceanography as a scientific community around like the 70s and 80s, a lot of scientists realized that there's no feasible way for us to sample the ocean, the entire ocean, and to understand exactly how the dynamics of the ocean are at every given point. It's just not feasible. So the Ghost Ship program was founded to um, establish a couple specific tracks, like a couple specific lines in the ocean that like all these countries would agree on that we would try to sample every like 5 to 10 years such that we could make sort of like a time scale of how the ocean has changed and when. And over time, if you're going over those exact same locations, and taking the same oceanographic measurements, then then you'll have a pretty good time series of the ocean. Which again, the ocean is just so big and so vast. So if you can't sample everything, you might as well sample the same spot every couple of years to understand how it's changing. And
Mhm.
so that's kind of the purpose of the Ghost Ship program. And it was brought I've always so most oceanographers know about the Ghost Ship program because it's a really rich data set. It's a really cool place to look when you're trying to understand like how the ocean has changed over time, um, just chemically and physically. And yeah, so any scientific cruise like this, they need a lot of people just to take samples and analyze samples. And I have always dreamed about going on an oceanographic cruise. I was very young when I decided I wanted to be an oceanographer. And since then I've just been waiting for that right opportunity to get onto a cruise. And someone told me about this in September of 2020. Um, and I applied and they could use me. And my advisor was really gracious in kind of letting me take, almost 2 full months off of my normal research work to go help out with this research program. And yeah, it was a pretty incredible opportunity. So that's what led me to the ghost ship. And the specific ship that we took was the RV Thomas Thompson. So that stands for like anything that has RV as a prefix is the research vessel.
Mhm.
So yeah, we took the RV Thomas Thompson and I was living there for about a month and it was pretty incredible. So I'm glad you followed along with the newsletters. It makes me really happy.
Yeah, definitely. And so I threw up on screen here just a little view of the different routes that are available, and you took the A20, right? Correct? And
Yes,
so
we took the A20.
right, so that's over here, right? Right in this area?
Mhm, mhm. So it's going, almost down the Mid-Atlantic Ridge. It's still further, it's further west of the Mid-Atlantic Ridge, but, it's down about 53 degrees, negative 53 degrees, longitude, and it's funny because, yeah, it's literally just a straight line down, and so we start kind of if you can think about it in terms of latitude, we're north of Canada, but still south of Iceland and Greenland, and then you go straight down through just the open ocean. It to the point where this is like the deepest the ocean gets, pretty much. We're going over the ocean basin, so it's like 6,000 meters. It's 6 miles deep. And then we went almost to the equator. We didn't quite touch the equator, but we basically touched South America and got really close to the Amazon River. And yeah, and then we docked in the U.S. Virgin Islands, and I flew home. So yeah.
Wow. Yeah, it sounds like an incredible experience. I mean, the opportunity to kind of blend together science with, a little bit of adventure or a lot of adventure, it sounds
Hmm.
like, just seems like a
Hmm.
wonderful opportunity. Also, just
Yes.
to give the ship to people who may have not seen it, this is the RV Thomas Thompson, so the research vessel, the Thomas Thompson, that you were aboard. Did you get
Hmm.
did you get seasick at all? I know I read in the newsletter that you kind of did, and you
Yes.
you did you put some sort of chemical or some sort of like drug patch behind your ear to help mitigate this. Uh,
Yeah, yeah. So the cruise, depending on where you're cruising when you're on an oceanographic cruise and what time of year you're going, you can get hit pretty hard. Most oceanographers, especially the ones that go to sea, generally don't get very seasick, myself included. But when we departed from Woods Hole, which is in Massachusetts, and it was mid-March, and so still very much winter. And then we sailed north, and winter in the North Atlantic is pretty brutal. So, yeah, they recommended, like make sure you get seasickness meds, and the most like common over the counter ones are like Dramamine, and that's just like it's kind of a depressant. But then there's also, a couple other ones, and they recommended we get sculpamine, which is yeah, it's a patch you stick behind your ear, and wow, it's heavy, like it just completely disorients you. Your mouth gets super dry and your vision gets blurry. It kind of like, it makes all of your senses much worse, but in an effort to like keep you from getting nauseous. So,
mm,
yeah, I definitely had to. It was the first, I would say, 3 or 4 days were really rough. But thankfully, and the issue with that, not only is it just like uncomfortable because you're seasick, but also you can't do science when the ship is pitching and rolling because the instruments that you're lowering off the ship are so expensive. And so if the conditions are too rough, you can't even do the science. And then it's just wasted time. So thankfully we only had like 3 or so days of bad weather. Yeah, and then we continued on and we got very, very lucky. But yeah, the Thomas Thompson, it's 274 feet. The boat is owned by University of Washington. Yeah, and it was just a really cool place to live and work and be. About 50 people were on board for my cruise. So yeah, quite the adventure.
you mentioned that the Thomas Thompson set out to kind of get temporal resolution and get different measurements of the ocean, like kind of analyze these parameters over time, like year by year. So
Mhm.
what specifically, is are they setting out to measure? Kind of what things are they looking for, and what information
Yeah.
can that provide to scientists?
Yeah, that's such a great question, Brandon. So, in the ocean, thinking about the ocean, separating yourself from the fact that it's this giant, vast thing. It's a type of water. And like all liquids, and I'm sure like most of your listeners are somewhat familiar with this, but all liquids are gas soluble. And so think about like your can of soda. You open up a can of soda and it's cold and there's bubbles in it. And what are those bubbles? That's carbon dioxide. And if you leave that soda in the sun, it's going to get hot and your soda is not going to be as fizzy and you're going to like degas and that carbon dioxide is going to leave. So I say all of this to give a little bit of context as to the ocean is a gigantic sink of carbon dioxide, and it is truly the engine of the climate system. The ocean is so important, and so changes in carbon specifically can tell us a lot about what the ocean is doing, not only like how hot is the ocean, but beyond that, how much energy is it taking in, how, where are things being distributed over time. So the primary objective of specifically ghost ship cruises is to study the carbon cycle. So apart from just carbon dioxide as a gas, we also sample for pH. We also, so to tell like the acidity of the water, and the more carbon dioxide, the more acidic water is. Um, we also sample for alkalinity, which is another kind of like deviation from pH. There's dissolved inorganic carbon, there's dissolved organic carbon. And all of these things are different parameters in a system that, we know the carbon system in the ocean, mathematically, we kind of can work out how it's supposed to go. Like we know all the chemical equations and how they relate to each other, but how it actually changes in the water is really interesting, and different variables can modify different cycles. And so we're primarily studying the carbonate cycle on these cruises. Another interesting part of the cruise though that I was somewhat expecting but didn't expect it to be so dynamic was we sampled chlorofluorocarbons. So for anyone that doesn't know, chlorofluorocarbons were a chemical invented in the 40s and the 50s, and they were primarily used as refrigerants, and they were very, very effective, but um, so effective also at destroying the ozone hole. So when these were emitted, they would get into the atmosphere, they would bond, they would basically make free radicals of oxygen that would end up eating ozone. So ozone is O3, and these free radicals, these individual oxygens, would get up into the ozone hole and
Mhm.
rip off extra oxygen. And so what was O3 and one free radical of oxygen ended up being, O2 and O2. So we got rid of, long story short, we get rid of chlorofluorocarbons. But chlorofluorocarbons are a gas. And just like carbon dioxide, like the ocean intakes chlorofluorocarbons. And so as we phased out chlorofluorocarbons after like some international agreements, they still remained in the ocean. So they're kind of like this layer that
Mhm.
you can track over time, because the ocean slowly draws water down. And specifically in the North Atlantic, this is one of the areas of the ocean that draws water all the way into the deep. So usually most of the ocean is really stably stratified, meaning it's super separated between the top and the bottom. It's like oil and water. Like the top is so light and so fresh compared to the bottom, which is so heavy and salty. But in the North Atlantic, it's close enough that it can mix between the top and the bottom. And so because we were sailing in the North Atlantic, we were tracking the chlorofluorocarbons and seeing like, okay, where is this, layer? It's kind of a pulse in time that you can capture. And just knowing what we know about ocean circulation, this layer of chlorofluorocarbons should in fact be deeper and, further in the water column than they were in 2012, the last time this line was sampled. And those should have been deeper than the time it was sampled in 1999. So that's another variable that we were measuring on the cruise as well. Um, so yeah, very interesting. A lot of chemistry, but primarily carbon. So yeah, that was
Okay.
what we were sampling.
Yeah, one of the gnarliest things just kind of reminded me of an environmental chemistry class I took during undergrad. Chlorofluorocarbons are gnarly, right? They like not only do
Yeah.
they react with oxygen to decompose the ozone, but they actually are a catalyst in the reaction, right? So they don't get consumed,
Yes.
so they can keep
Yes.
going on and keep decomposing the ozone. So it was a really gnarly problem that
Yeah.
we had to stop using those. Um,
Yeah.
and so one of the instruments it seems that you were kind of primarily responsible working with on the Thomas Thompson was the CTD rosette, right? So
Yes.
CTD being conductivity, temperature, and depth.
Yes.
So can you describe this machine a little bit in more detail and kind of your role in working it?
Yeah, totally. So yeah, in chemical oceanography and most oceanographic cruises, the primary method of measurement that we have is raising and lowering a CTD rosette. So um, CTD standing for conductivity, temperature, and depth. Essentially, why do we care about those things? So conductivity is you can measure actually the salinity, so the salt content of water by measuring its conductivity, and that's actually a really quick way for you to be able to tell how salty is this water. You pass a tiny little current through a tiny little sample of water, and you get the salinity. And then you also obviously you want to know the temperature and you want to know the depth of that water. So on this big machine, so think of it's a little bit, it looks like a little bit like a like merry-go-round, but it's about like 8 feet, 9 feet tall, and it's circular. And we have one machine on the bottom that measures conductivity and temperature and depth on this metal machine as it goes down into the water column. Now, that's only one component. The rest of this, like little merry-go-round, is actually covered in tall, skinny bottles. So these bottles have openings at the top and the bottom. And what we do with the bottles is we lower this machine all the way down to the bottom of the seafloor. And the whole time we're measuring conductivity, temperature, and depth with just this little device, and it's sending data back up to the ship through a wire. Once we get to the bottom, then we slowly raise this whole machine and we close the bottles at specific depths. So if you think about at the like sea floor, if we have 36 bottles, we're going to close one bottle. And once you close that bottle, you have now captured what the water looks like at the bottom of the ocean. And then you raise your machine a little bit more. You raise it maybe like 200 meters, and then you close another bottle. And so you continue to do this kind of in a spiral all the way until you get back up to the surface. And the purpose of this being that you have an exact picture of what water is doing at each depth of the water column. And then you pull it back up onto the ship, and then you take very detailed samples then of each bottle. So then my role in this excursion, so I wasn't really actually doing any of the chemistry. I was helping raise and lower this instrument and decide when and where we would close bottles. So that's kind of an art in itself because you want to make sure to capture really interesting features of the water column. So for example, like obviously you want to know what's happening at the bottom, but you also want to see what's happening, say, at the end of the euphotic zone. So this is the end of the area where sunlight can no longer penetrate. Usually this is a really interesting place for carbon, for the carbon cycle. So it was my job to first of all take care of this device and clean all the bottles, caulk all the bottles. They're under incredibly high pressure, so you have to pull these springs back, and it's pretty physical. And so I have to clean the bottles and prepare the bottles. But then once it's getting lower down to the water column, it was kind of my job and like my fellow operators, we would be on the radio with the crew members operating the winch and telling them what depth to go to, when to stop, and then we'd use software to close the bottle, make sure that that sample is truly tightly cataloged in there, and then keep on bringing it up. And so for some of the to give context as to like, okay, that sounds it, and it's in practice very simple, but it just takes a long time because the ocean is so deep. It's crazy. So even if you're lowering this device at 60 meters per minute, um, some of the full down and up, sometimes it took almost 5 or 6 hours to go all the way down and all the way back up again. And then the second that that instrument hits the deck, the second we get it out and safely secured on deck, two things happen. One is that the ship is full steam ahead to the next station, because we do not want to waste any time. And the other thing is that then all the scientists come out and we're all in the sampling bay. So it's kind of like this, it looks like a hangar, it looks like a garage. And everyone brings all their sample bottles out. And then it's my job to tell everyone in what order to sample these bottles. So it's not as simple as just then opening the bottle and like, oh, okay, I need 10, 20 milliliters of this sample, but actually certain samples are really gas sensitive. So if you think about at the bottom of the ocean, you are under such immense pressure. It is so much pressure when you're under 6 miles of water on top of you. So once these bottles make it back up onto the surface, it's super important for the validity of the sample to go as quickly as possible because once it's exposed to the ambient pressure of just like being back like on the surface, it's going to change the way that the gas interacts in that sample. So it's my job then to help the scientists sample in the correct order and go as quickly as possible around this rosette, but not too quick because if someone is super speedy and they've made it to bottle 10, but the person sampling pH and pH is gas sensitive, if the person sampling pH is still kind of lagging behind, you don't want someone to get too far ahead because then the pH sample is going to be um, like compromised.
Right.
So that was kind of the other job, was just to make sure like everyone's going in the right order at the right pace. Yeah, and then doing it all over again 90 more times.
Yeah, the gas sensitivity of these samples is really, yeah, totally a thing. It's funny. Just the other day, a postdoctorate, so a very educated lady in my laboratory, was like, "Brandon, I don't know what's going on. Like, I think the pH meter is being weird because I'm trying to take the pH of
Mm,
water and it's not 7." And I'm like, "Well, it won't be, right? Because CO2 will dissolve in the water and you'll make carbonic acid, and so it's actually going to
yes.
be pH around 5.5." And so, yeah, if any of the atmospheric gases or stuff dissolve in your sample, going to totally change things, and the pressure difference will also change things as well, which is funny, just
Yeah.
that somebody who can be such a senior scientist would be like, oh, the pH of water isn't 7. It's like, no, not really,
Yeah,
in an ideal
yes.
space. But just to kind
Yes.
of clarify some of the things you said, because it's really just a crazy engineering feat. So you're saying that this like multi-million dollar machine, which measures conductivity, temperature, and depth, gets winched off the side of the boat
Yeah.
and dropped into the ocean some like 4,000, 5,000 meters deep, and is somehow able to withstand all that pressure. Uh,
Yeah.
wow, that's crazy.
It's incredible, and I also think too, it's cool to see, and I mean, it's like it's very sturdy, and everything on the, all the bottles are super sturdy, and it's all thick. But to me, it's more the instrumentation that's on it. There's some really incredible sensors that are on it as well, and so with like CTDs, usually people also like put extra instruments on there if they can. So um there was another instrument on there called like the ADCP, which is like acoustic Doppler scanner profile or something. But that instrument does like sonar to measure the size of particles or the speed at which particles are passing through. And all this is to say is like it's amazing that it goes so deep in the water column under so much pressure. And then there's also, yeah, all of these like electrical and mechanical things just just going the whole time. So yeah, I mean, it's quite a feat. And some this not this rosette, but some rosettes that they take like they can take them even deeper. They can take them to like some of the deepest parts of the ocean, so like 9,000 meters, 10,000 meters, which is crazy.
That's crazy. And I don't mean to, romance the job too much because it definitely seems like really hard work. Like you mentioned, even just taking out, like unscrewing these water columns is like, I read in your newsletter, some people like broke their hand because like the screen
Yeah.
would break on them. So yeah, it's pretty gnarly. And then it's what, like a 12-hour shift each day?
Yeah, so, that's kind of like the whole part of this, like, it's funny because it's called a cruise, right? But it's not like a pleasure cruise. These oceanographic vessels are so insanely expensive to operate. It's a lot of money for insurance. It's a lot of money to operate a boat like this. These boats are incredibly, um, they're literally made for science. And if you think about too, like this instrument, for example, like the CTD is like over $1 million. If the ship were to move and like compromise the CTD, if it were to move, like to drift with the current and pinch the wire that's holding it onto the ship, it would break and fall off. But then think about this is a almost 300-foot boat in the middle of nowhere that has to stay completely still for 5 hours. So the ship has really amazing like thrusters and it's just yeah, it's really a marvel of technology, but it's super, super expensive. So it operates 24/7, 7 days a week. There is no, there's some, but pretty much no downtime when you're on a ship like this because, yeah, you just like don't want to waste a second. You don't want to waste a sample. But it is really beautiful, like the kind of like brotherhood, the camaraderie of everyone on one of these ships, like you know what you're getting into. And if you don't, you learn very quickly. I don't know of many other like professional scenarios where you're literally, you're living and working. It's like summer camp, but you're all oceanographers and but it's also kind of like being in a sorority because you all live together. It's a really wholly unique social and professional scenario that yeah, it's exhausting for sure, but really, really fun and quite addicting for some people. Some oceanographers are totally hooked.
Hmm. Yeah, it was. You kind of did a segment. I'll get to this question with you in a second. But you asked at the end of your cruise, you asked everybody kind of how what got them into oceanography. And
Mhm.
one of the people, I think it was like the lead oceanographer on the cruise. I don't remember his name, but you asked him. He's been going forever. He's been doing these trips forever, and you're like, do you like it? Do you still like it? And he's like, oh, I love it out here.
Yeah,
Which I could
yeah.
I could totally understand because it just seems like such a sense of an adventure. And if you can kind of get past that, I don't know, that isolating feeling, that could be, I don't know, I could imagine you get a little isolated, but it might be really nice to take that break from society.
Oh, yeah, and I think a lot of oceanographers, they either love it or they hate it. Um, and it was really cool, yeah, to kind of ask everybody, especially people that are seasoned. Most oceanographers that are on these cruises have done like 10 or 20. They might do one a year, which is a lot because these are like at minimum usually a month long, sometimes two, sometimes three if you're going somewhere really remote like the Arctic. Um, so yeah, it is a really cool dynamic that builds up where you're all just unified towards a common goal, right? It's just like get those measurements, get them safely, make them good. But yeah, it's isolating in that way, but it's also incredibly unifying because you all are here for this one thing and it's also this camaraderie of like you're all cut off from society. And it was very interesting going on this cruise during COVID and like lockdown because so we all had to isolate, we all had to quarantine for 2 weeks before the cruise. And I mean, pretty much, and also we just hadn't really been seeing each other, anybody really before. And then to get onto a ship with 40, 50 people, which I haven't been around 40, 50 people since before COVID. And so to then be all together again was really interesting and like very cool. And I think all of us just like it was, I think, a particularly special cruise because we all had been so deprived of that connection for
Mhm.
so long. And then to be connected with so many new people that are so inspiring and also like just motivated by the same things that motivate you was really cool and unique too. But yeah, it takes a different breed to
Yeah.
do the whole cruise thing.
It seems like very like quickly when you're reading the newsletter, it seems like yeah, there definitely is a sense of community on the ship, right? I mean, you like you said, you know, you have this, you're isolated with these people, and like that's it, that's your world, and so you really have to like get along and communicate with these people effectively.
Mhm.
And yeah, going off what you said, like you know, cruise people are built different. One of the gnarliest things that I kind of read about in the newsletter was when the winch got stuck. So when the CTD was
Mhm.
over the side and the winch gets stuck, and then engineers have to come out and like on the fly fix it. You know, you can't, you know,
Mhm.
because you can't lose any time, right? You know, this is money, money is time, and so it's like, oh, you got to fix that on the fly. That seems so just gnarly and like exciting. Like, what an exciting like problem to
Yeah.
tackle right away.
Yeah, for sure.
So that's a lot about the Thomas Thompson. There's just so much to talk about.
I know, it's crazy.
What would you say is like the best experience you had on the Thomas Thompson? And then also, you know, what is maybe the worst thing that you kind of went through on the Thomas Thompson?
That's a good question. I think I think kind of the best experience was, I would say in general, my position as the like CTD operator was really unique in that I got to talk to every single one of the scientists to get to know them and their sample and what they needed. You know, is their sample gas sensitive? Is there things that I can do to help them sample better? So that was really cool to be able to get to know all the scientists and then all their measurements too. I like, if I had any extra time, I'd have them talk me through their sampling techniques and then see, how do they actually make these measurements. So I had that interaction with all of the scientists and then additionally with the crew because the scientists and the actual crew that's operating physically the ship um can get kind of like separated in this whole process because the crew, their job is just to get the ship from point A to point B as quickly and safely as possible. Whereas the scientists, they don't need to worry about that. They just need to worry about their samples.
Mhm,
And so a lot of the scientists and crew end up being in these separate pockets.
mhm,
And I felt very lucky in that I got to almost completely equally interface with both because with the crew, we'd have to communicate like, oh, okay, our next station is here. We need to be at these depths. The CTD is giving us funny readings. Like, do you think something's going on with the electrical? Like, so that was really awesome to be able to like have, dip my toe into both worlds because I think a lot of scientists just get they come out to take their samples and then they go back into the lab and then they're full steam. Then the whole time that I'm interacting with the crew and other people, scientists are just going to make as many measurements as possible and not get behind. So I would say that's probably my favorite part. In general. And there were some other really amazing memories too, like when there was a specific latitude that we got to that's sometimes referred to as the doldrums, but it's where the atmosphere interacts in such a way that it makes this dead zone of wind. And so it's this band of ocean that's flat as a lake. It's gorgeous. And the doldrums were like in pirate times very dangerous because they were all sailboats. And so if you got stuck in the doldrums, like you could, be stranded for weeks. But now it's really great because, we showed up and the water was just so blue and glassy. And then those nights when we were steaming to the next stations, there was phytoplankton in the water that was bioluminescent. And so it was really cool to stand on the stern of the ship and look as the rotors churned up water. It was just like little light shows. And that was just really special, especially when you're so tired and kind of deranged and just like in this completely foreign environment, and then you're just looking into the water and it's like explosions and you're like, what's going on? So that would be another favorite memory. And I think in terms of difficult times, it's just you can't have a bad day on a ship because there's nowhere to go. Like,
Mhm.
what are you gonna do? Like, jump off? You can't do anything if you're in a foul mood. And so there were a couple days where like just the attitude or like the demeanor of someone else can just have just this cascading impact. And so um the dynamics of the ship can really shift. And there were like 1 or 2 days where the scientific party, I think, was just having a bad time. And you could try to track it down to one specific thing that happened, but then it just like the ick spreads. So yeah, that was a little bit difficult, but eventually, like, and I think again, like, people that do these cruises know, they know what the deal is. Like, maybe we have one bad day, but like you can't keep your attitude. You got to wake up the next day and just like blank slate, start anew, because if you carry a bad attitude for more than 2 days, it feels like a lifetime on the
Mhm.
ship. So, yeah, that would probably be the most challenging part, is just like making sure that, like, that bad attitude, whoever's it is, doesn't completely impact everybody.
Yeah, I mean, in the newsletter, you definitely mentioned kind of towards the end there. You mentioned kind of these negative days that were happening, or like kind of got negative attitude that was spreading, and I
Mhm.
got kind of concerned. I'm like, oh my gosh, I hope that's I hope it's not bad. But then kind of like the next week's issue of the newsletter, you're like, you're kind of like the reflecting on the experience as a whole. You're like, yeah, for the most part, 99% of the time, it was awesome. And
Mhm.
with such an amazing experience, I'm curious, how you got involved in it, and then also, what people can do if they're interested in how they can get involved. I know that if you go to www.go-ship.org, you can reach out to the person who is the correspondence for you. You can try to set it up, but how did you sign up for a cruise, and how did you find yourself on the Go ship?
Yeah, yeah, it's a great question. So I heard about this specific call for like needing kind of graduate students, kind of students to help out. I heard about it from a friend who's in my lab group at UCLA, who he used to be a marine technician on these oceanographic cruises. And he heard like, oh, they're looking for people. And so there was like a flyer getting kind of circulated, and I believe that they also released it on the Ghost Ship website. But he was the one who told me and was like, you should apply for it. And then if people are interested, there's a couple different programs, not just Ghost Ship. If you're interested in doing like any oceanographic cruises, because this is just one flavor of oceanographic cruises, because there's so many different kinds, which is super cool. There's one that I really love in particular. It's called the Nautilus, and it's run by the Ocean Exploration Trust. But the Ocean Exploration Trust was founded by Dr. Robert Ballard, who is the guy who found the Titanic. And he has a ship and he takes student interns every year, and he's really passionate about that. NOAA, the National Oceanic and Atmospheric Administration, has positions on ships for students. And they put out calls every year. Usually for the summer internships, they ask around January, and things have gotten kind of backlogged because of COVID. A lot of oceanographic cruises got their timetables got all messed up.
Mhm.
So I feel super lucky to have found this one when I did, because the chances in the next year, probably the cruises are going to be kind of rocky because they're trying to catch back up. But yeah, it I don't want to say that it's only word of mouth, because it's not, but it's also, you have to actively search for like oceanographic cruise intern. You have to kind of dive in. But yeah, it's a really amazing experience.
Awesome. Yeah, it sounds like there's a lot of resources out there, and people just really need to be excited
Mhm.
about and seek them out. And
Mhm.
I'll definitely look those up and post those in the link in the video when I finally
Sweet.
post it. Um,
Sweet.
so kind of what are some of the major takeaways, like wrapping it up, wrapping the research vessel experience up? What are some of the major like experiences that you took from this cruise?
Yeah, it's a great question. So I think major takeaways are that you know, like the oceanographic community is so amazing and so passionate. Um and and that you have so much to learn from every single different scientist and their perspective. Um I've also taken away truly how complicated the lab sciences. So I'm coming from my background is actually more computational. Always been interested in oceanography, but I'm more on the side of the math and the physics and like the mathematical quantification of ocean processes. I never really did very much sample work, but seeing people doing the sampling and doing the chemistry and it's so complicated and really impressive. So I have a way profound appreciation for every single sample that's taken because it is a lot of work. It's a lot of repetition. Yeah, and another takeaway too is just that I think I do see myself being an oceanographer in the long term. Like even some of the more senior scientists on the ship, just hearing them talk about their careers and, that they still love coming out on the boat. And, it was just real, that was really inspiring. So I hope to emulate that energy and continue on for the rest of my career.
Very cool. And so now I kind of want to zoom out, get away from the research vessel experience, and give a little bit more just personal background to your life. Show the audience, how does one become, a successful oceanographer. So can you tell me a little bit about like your career path and how you ultimately became a scientist and how you became interested in oceanography? Was it one moment that you can pinpoint, or was it kind of a culmination of things?
Yeah, I'd love to. So, I'm one of those like terribly annoying people that I was like 4 years old when I decided I wanted to do oceanography. So, actually, my parents had bought it's like a National Geographic documentary about Dr. Robert Ballard, the man who found the Titanic, finding a different ship, the battleship Bismarck, and but the whole documentary is about him on this oceanographic research vessel, and they're using this technology that's now super outdated, but in like 1999, I'm watching this. I'm 3 years old, and it was the coolest thing in the world. And I always loved the ocean. I always was just a water baby. I would just, sit in the ocean, and I loved the feeling of waves. I loved like going just beneath the surface and like letting the ocean kind of rock me around. And it always really fascinated me. So it was kind of decided. And once I, was like, oh, oceanography is like a career. Great. I'll do that. And it helped that, as I continued through school, um, I was really good, but not really good, but I was proficient at math and science and physics to the degree that you kind of need to be to have it not seem so intimidating. So, yeah, I was always, really inspired by oceanography and oceanographers. And yeah, then it was never really a question in my mind. And so when I was at UCSB for my undergrad, that was a perfect place to be because it's literally on the ocean. The campus is on the ocean. You can't get any better than that. And in terms of oceanography, it has some of the best faculty in the world, in my
Mhm.
opinion. And I was very lucky in that I started in the earth science department. So interestingly enough, we don't have an oceanography major at UC Santa Barbara. There's marine biology, but that's different. That's more like the living,
Mhm.
like mammals of the ocean. But yeah, so I started off in the earth science department, which was super cool because that gives you kind of a truly geologic scale of the ocean and the climate and how they've interacted over, the last 4.5 billion years of Earth. And then I branched out into the geography department and added on a physical geography major. And both departments did a really, I think, holistic job of teaching the math, the physics, the chemistry, and then how all those things couple together and make the ocean the dynamic engine that it is. So I was just so inspired the whole time, and I was really lucky to take some amazing classes. And then it was no question that I would continue. Um, so then per the recommendation of like many trusted mentors, I took a year off between undergrad and grad school, because I just wanted to take some time to like, take a break from academia and like work. And also too, I know that like you're just finishing going through like the grad school process. It's exhausting.
Mhm, mhm.
So I wanted to like make sure I was ready for that. So I took a year off and I worked at the National Center for Atmospheric Research, which is like also abbreviated as NCAR, but it's kind of the way I describe it, it's like NASA but only for the atmosphere.
Mm,
So it's operates somewhat like a university in that it's primarily funded by the National Science Foundation and grants. But that was a really amazing place to work. While I was at UCSB, I got a pretty deep GIS background that's kind of what I used when I was working at NCAR. But yeah, that was a really amazing time. Had a year, had so much fun, lived in Boulder, Colorado, which is awesome. But yeah, and then, you know, during that time I was thinking about grad school and uh deciding, like which beach school am I gonna go to. But kind of by surprise ended up at UCLA. I was expecting either to go back to Santa Barbara or go to UC San Diego or maybe Santa Cruz. But I met my advisor almost at the end of my PhD application process, like almost like a week before the UCLA application was due. But he had the same, like, we shared the same passion for the ocean and specifically what I wanted to do, which was like modeling and biogeochemical cycles. So understanding how the biology and the physics and the chemistry all kind of couple together and not really focusing on one specifically. And he, was so enthusiastic and I was completely sold. So, yeah, applied, toured, got in, and yeah, then it wasn't a question from there. And so I've been at UCLA ever since
very
and I love
cool.
it very much. Yeah.
Very cool. And so that advisor that you're under currently is Daniel Bianchi, right?
Uh-huh. Uh-huh.
So what is, what is the focus of your graduate studies right now? What are you looking at? You kind of mentioned it just a little ago, but could you go into a little bit more detail into your day-to-day, what your research project is?
Yeah, totally. So, so my group at UCLA, we like, I guess, all generally operate under the blanket of we're all biogeochemical modelers.
Hmm.
So, what I specifically do in that, kind of niche sounding domain is, I look at the Southern California Bight, so the area starting from Point Conception down to the border. I look at the coastal region, and specifically within the coastal region, what I want to understand is how our wastewater impacts coastal productivity and coastal distribution of species and ocean acidification and deoxygenation. So, the way in which I do that, and we do that in our group, is we have this giant, amazing physical model of the ocean, which is it's abbreviated as ROMS. It's the Regional Ocean Modeling System, and it's written in Fortran. It's this crazy computer program that, I mean, think about it. The ocean is so dynamic. The fact that we can physically model it is insane.
Hmm.
So we have this physical model, but then our group also has a set of chemical equations and biological equations that we can couple to the physical model. Um, and so we couple those and we send all of that information. We package this huge program and then we send it off to a supercomputer somewhere. And then it gives us outputs. And then we analyze those outputs. And specifically, I'm looking at wastewater. And so in Southern California, we have four major treated wastewater outflows. So the way that we deal with our wastewater is there's something like 22 million people living within the coastal zone of California of Southern California, I should say. And all of that excess wastewater is treated usually secondary. So meaning it like all the organic matter is removed. It is like not poop water anymore, but there's still nutrients. There's still ammonia in this water. Another thing about the water that's interesting is that it is a completely different salinity than ocean water, obviously. And it's a different temperature. And you might, it's like, okay, interesting. It's got a little bit extra ammonia. And so each of these pipes that, they treat the water and they pump it back out into the ocean. They try to pump it back out decently offshore, like 100-ish meters offshore, depending. And then they try to pump it out very deep. So at like 60 meters, 60, 50 meters. And they hope that the deeper they pump the water out, that it's below where the primary like biological productivity is happening so that it won't really influence the biologic
Mm,
cycles of phytoplankton growing and zooplankton eating the phytoplankton and all that jazz. But there that's not so straightforward because the California current system has so much mixing. It's very turbid water. So a lot of those nutrients are brought up to the
mm,
surface. Another reason why those nutrients are brought up to the surface is because it's just more buoyant. It's not as salty as the
mhm,
surrounding water. And so you have this buoyant plume of water that it's not toxic, but it's just different.
mhm,
And so it's going to cause changes in its like surrounding area in terms of productivity at least. So my research right now is understanding what those changes are and if water, if we are to treat our water in different ways, if we're to change the standards, what's the most efficient way to do it? Because water treatment is so expensive. And to say that we need the water to be 100%, clean is unfeasible. And also too, if you're pumping out just straight fresh water, that's also going to impact the current in like the California system because it's not ocean water. So
mhm,
my primary research is to study that. And then a little tangent that's I'm not leading on it, but people in my group are working on is understanding too then how those changes can also trigger harmful algal blooms. So
mhm,
there's certain species of algae in the California current and all over the world that under certain stressed conditions they'll just start producing a toxin.
mhm,
And the mechanism is a little bit foreign. We're still trying to understand it. But in the California current system, we experience harmful algal blooms and toxic algal blooms, and that can poison seabirds, sea lions, poisons people. So we're also trying to be able to model that as well, like kind of coupled to our already established physical biogeochemical models, and we also want to make as another kind of addition to that to say like probability of a harmful algal bloom happening in the
mm.
California current. So yeah.
Very cool. It almost sounds kind of like a very, I mean, not direct platform off of, but very related to your work during undergraduate, where your thesis was what was it, monitoring the threat of runoff to coastal ocean environments, right? So kind of like, you're still very interested in the coast, and you're still kind of looking at,
Hmm.
like runoff slash wastewater and how it impacts the ecosystem.
Yes,
Very.
definitely. I've always been like I think coastal dynamics are so interesting. It's like it's where we meet the water, but it's also they're super sensitive systems
Mm,
and yeah, and it's we're doing so much like humans are just like completely altering these like chemical and nutrient cycles. So it's very interesting and I think important to understand like what does that mean not just for like the trophic levels of the ocean but like for us as humanity, like what's going to happen as we change this water. So yeah, I think I'll probably stay on that same vein too for as long as I can. I always have more questions every day.
very cool. Okay, so another personal question. We touched on it a little bit earlier, but you obviously have a lot of passion for not only science, but also scientific communication, uh, with your newsletters, and then you have this research vessel newsletter, but then you also kind of had one called "Climate Change for Cool Kids During COVID," kind of
Yeah.
a 2 month long lecture series where educated people in a conversational way, easily digestible way about important topics involved with the climate. Um, and this is all just you taking it upon yourself to like teach people about the climate and just raise scientific awareness and scientific participation. So, and I
Hmm.
must say they were fun. Like they were definitely. I mean, I wasn't
Thank
in the
you.
live interview, but there was like little drinking games, like take a drink every time I say CO2, stuff like that. Very engaging,
Yeah.
and
Yeah.
so many analogies, like with the soda can that you brought up earlier, and things like that to really you know make it easy and not, obfuscate it with jargon and, a lot of like big words and scientific terms, but really just, be poignant about it and communicate, in a way that everybody can understand. So
Yeah.
where did this like passion start, and like why are you
Mm.
so committed to scientific communication?
Oh, that's a good question. Well, first of all, thank you for your kind words. Yeah, I've always just been a big science nerd. I don't know if there's like, I can't remember a time where I wasn't fascinated by science in general. And I think I've always been like very outspoken. I've always just loved attention too. But I love teaching. And I think it's been very fun to, as I've grown and just gotten older and learned more, it's really something that brings me so much energy to pass on the amazing things that I see. And I get so geeked out about like the earth and the ocean and all these things. And I think it's been a big failure of science to not make so many of these things more accessible.
Hmm.
And I know that the true joy that I feel when I can get someone to see like, here's why I'm so stoked about that cloud. This is
Hmm.
why that cloud is actually crazy because here's what's going on in the atmosphere to make that cloud. And then, to bring people into that joy that maybe they then will someday see that specific type of cloud and be like, "Oh my god, like that's amazing that that just formed." Um that just like gives me energy every
Hmm.
day. Specifically, climate change has been, I feel very lucky to be a scientist right now, and specifically one that's interested in the climate. Um, I'm, at UCLA, ITA, our like intro to climate change class, like atmospheric and oceanic science one. It is a big GE, and it's almost wholly non-majors. So we have
Hmm.
like theater majors, business majors,
Mm.
public health, econ. There might be a little sprinkle of someone, a couple people in physical science type majors, but um I love it because it is an opportunity to just like actually explain how incredible the earth is. And the fact that the earth even exists just blows my mind. And then, here's why it's so complex, how it's changing. And here's why, you should never take any like, you shouldn't take things at face value when you're told all these things about like the climate, here. And also here's why we're all scientists and we're all worthy of understanding what's going on. None
Mhm.
of this information you shouldn't I don't want anyone to ever see like, oh, I'm not capable of, understanding this. Obviously some things get so convoluted and some things are kind of, beyond the realm of like needing to understand for the average person who's interested in the climate. But
Mhm.
I think everyone is capable and everyone should know that. And everyone has a right too. Like we're all humans on this earth. Like we're all guests
Mhm.
here. So no one should be gatekeeping that information about the earth. Like, oh, if only you knew more about,
If only you went to school for 10
chemistry.
years, and then I could tell you all the secrets. No. And
Right,
and
right,
you touched on
exactly.
it a second ago, but kind of the failure of like modern scientists, not everybody, because certain magazines are doing a great job and certain kind of video outlets are doing a good job. But I mean, if for example, during my graduate school applications, right, if I want to learn about a lab, I have to go to their lab website, and the best thing you can really do is read through all their publications. And nobody
Mhm.
just has like, maybe some people do, like one or two that out of the hundreds of labs that I looked at, but nobody really has like a YouTube video or like just
Yeah.
a graphical representation of what they do. And it's just, you get buried in all this jargon, and it cuts off
Mhm.
normal people, not normal people, but people who aren't scientists by profession,
Yes.
and it makes them feel like they can't interpret the data or even really understand the data. And it's honestly sad because nothing should really be
Yes,
so complicated that you can't explain it to me. You should be able
yes.
to elevator pitch what you do to me and to really anybody. And, as long as their IQ is like above 70, they should be able to get it, right? Like
Yeah,
it's a
yeah.
shame that like the scientific community, like you said, kind of gate kept a lot of this information for a long time. And it kind of goes back to your presentation at Esri, ESRI. I don't
Mhm.
know if you say Esri, but you gave this presentation about your thesis in undergraduate, and you talked about how you assembled this great tool, uh, to analyze and kind of like give a graphical representation of all the data that like was built up in the years, and all the data is like decades old that you're using, right? It's like old and available, but there's just
Yeah,
no
yeah.
good visual representation of it. So it's like almost useless, right? Because it's only relevant to a scientist who will dig through it for hours and hours.
Mhm.
But if you have, a wonderful, like the picture you made, right? The geographic information system, or that story map that you made, uh, really just boils down all that data into just one really easily understandable graph that like anybody could look at and understand what it's meaning, right?
Mhm.
And so, yeah, I think more work certainly needs to be done in terms of scientific communication and like getting people uh, to actively participate in the scientific community.
Yeah, yeah, and I think yeah, I think we share the same sentiment in that regard, when especially when you're pursuing higher education and it's like, oh, so exciting, you're at this level of learning, I guess, and research, but then it seems like a failure because, for the rest of it's like, oh, let me tell you how great all of our research is and everything that we do. And it's like, okay, could you explain this to like the average person? And also, like, do you believe the average person is like worthy, right? Like,
Hmm.
is that something that's a priority to you? And just to a lot of scientists, it's not.
Right.
And I think it's a little bit a product of, certain generations. They
Hmm.
just are like, I'm a scientist through and through. I make my science for other scientists and that's science. And
Hmm.
that's not the science that I want to be doing. Not to say that it makes their science less valuable, but it makes it less valuable to humanity.
Hmm. I
And
mean, it definitely makes it less valuable. I mean, less people that get to see it. Yeah, I mean, it is less valuable. Like people, it's not
yeah,
going to
and
have an impact.
especially for me in my field with climate change and climate change related things, I think that is completely inexcusable to not make it incredibly applicable to not just the public, but to policymakers, but to
Hmm.
people who need to hear what's going to happen and how we understand what's going to happen,
Hmm.
or even what we now know we can't predict what's going to happen.
Hmm.
We are responsible as scientists to be able to tell people about those uncertainties, about those changes because like humanity is going to change and yeah, and just to keep that information from others to me you know, is very inhumane. But then and then on the opposite side of the coin to share that information with everybody and to explain just like what makes me so excited is so fun.
Hmm.
It's so fun. So I try to yeah, I've been trying to find ways to continue to incorporate that into my life, but and you're literally doing this, right? You're doing a podcast. This is like an amazing form of communication. Um, and as I've gotten into like higher education, you definitely like you have to take it upon yourself. There's aren't many people who are like, a big part of our lab is outreach. Like a lot of
Hmm.
labs may say that, but in practice it does take a lot of effort. So it's something that I've very consciously curated, and and it's exciting, yeah, to see you also like consciously curating it because we need people to yeah, we need to break down these walls.
Yes, definitely. So kind of platforming off that, what's some advice you might have for a young scientist, maybe someone interested in
Ooh,
oceanography or just a general scientist, just trying to
yeah,
get their career started.
yeah, that's a good question. So for I'll start first with the specific of like an oceanographer. So if you're interested in getting into oceanography, um, like people hate when I say this, but it's like learn the math, get comfortable with the math, get
Hmm.
comfortable with physics, get comfortable with all the things that may seem kind of heavy,
Mhm.
because it is so much. Oceanography is so process based. I know, and it's funny, people always ask me like, "Ooh, tell me about, you know, shells or like marine biology." I know nothing. I have not taken a biology class since freshman year of high school. I know
Mhm.
nothing about biology.
Mhm.
So this is specifically for oceanographers, but yeah, get comfortable with the math and the physics. Um and really take your time, try to find a part of the like oceanographic cycle that you are, try to find one component because all of it is so amazing, but you'll get lost in the weeds if you're too interdisciplinary. And I'm super interdisciplinary. So if you can find one specific component that you're hooked on, pursue that. Um, for a general scientist and for anyone kind of coming out of so for anyone in undergraduate currently that's interested at all in science, I'm sure you would echo this, Brandon. Just do research,
Oh yeah.
do anything with anybody,
Mhm.
knock on doors, send emails. Also, I think one of my biggest lessons was that like you don't need to fill out an application. You just got to go talk to people. Like
Mhm.
you just got to go into a lab, ask people what they're doing, see if they need help, they know of anyone that needs help. Um, Doing research is so invaluable, and I think it's something that a lot of people for just don't do, or they
Mhm.
don't take the priority to search that out.
Mhm.
And you can't recreate that once you're out. It's really hard to get research experience once you're out of college, without having any previous. It's kind of one of those terrible cycles.
Mhm.
um,
It's a catch 22, definitely.
Exactly, exactly. So especially while you're in a university, get research experience. Again, if you're in a university, go to office hours. You don't have to say, if you ever have a teacher that you find mildly interesting, go just say what's up.
Mhm.
Go say hi. Like go week 3 of the semester or the quarter and just say like, "Hey, I'm taking your class because of this, and I'm interested about what you said the other day." Whatever. And professors appreciate it. They'll give you their stories. They might put you in some really interesting research themselves.
Mhm.
So yeah, again, just like take advantage and like,
Mhm.
yeah, just don't waste that time. Getting into the professional world, more difficult. I mean, yeah, I was kind of lost the year that I was doing research as like a professional. I felt much less guided. And I don't know if that was a product of just where I was at or just the fact that when you're doing independent, research for the first time, truly independent research for the first time, you just feel very lost. So try to have some touchstones and try to have some bigger goals in mind other than, I want to do research. Try to have some really tangible goals of like, I want to get proficient in this software by
Mhm.
this date.
Mhm.
I want to speak at 2 conferences this year. I want to, like be up on the literature on this specific thing. They don't have to be massive goals, but defining what specifically they are can really help in times that you're lost. So yeah, that would be, for scientists starting out, and any job is a job, any research is research, even if it's not specifically that thing that you were looking for.
Mhm.
You're going to learn so much and make so many connections.
Mhm.
So that would be my other advice too. Just be like, go for it. Take the opportunities where you can get them. Sometimes it's a painful process to get to those opportunities.
Mhm.
Um, but once, search them out, they're out there. Once you get there, take advantage, like hold yourself accountable.
Mhm. Yeah, I would definitely agree with all that. Research is tremendously important because it's so difficult to get that research experience, which most jobs require kind of after
Yeah.
school. Um, yeah, totally agree with everything you said. Yeah, that's all great advice. And now you're so successful, right? I mean, you've just had such a decorated career so far, and it seems like it's only going to keep going.
Oh,
Uh,
thank you.
and like we can often get caught up in, oh man, this person is so great. Are they just better than me? And so I think it's a helpful exercise and helpful to try to ask, what is your greatest scientific failure? What's a time where it didn't
Yeah.
work out for you, and how did you respond to that?
Oh my gosh. Well, yeah, thank you for the kind words. And it's funny that you say that because imposter syndrome is so real. It's so real, especially, at like any, you're doing research, you're at a university and you're just like, the more I learn, the less I know. The more I
Mhm,
learn, the more I'm like, I'm an idiot. I don't know
mhm,
any of this.
mhm,
So like an example, I mean, I literally last week just got a no from a fellowship. I've applied to, I think, 8 fellowships now.
mhm,
I'm lucky that I'm funded by UCLA, but I've applied for the NSF-GRFP twice, gotten 2 no's. I've applied to the same NOAA fellowship twice, gotten 2 no's. I've applied for the DoD fellowship. I've only been denied fellowships except for one that was like kind of, but that was more like interdisciplinary for, like leadership stuff, which was
mhm,
I'm super thankful for. But um so first of all, denial is so common. People don't talk about it enough. Everyone gets denied a lot. A lot, a lot, a lot. So I am absolutely no exception to that. I've had, so my like senior thesis, I am still trying to get published
mhm,
and it's
mhm.
painful. It is nails on a chalkboard. And at this point, like I wrote that like 3 years ago and I'm so sick of it. But
Right, right.
yeah, but it's like, oh, it's such a slog. But yeah, it was rejected from, oh gosh, I forget what journal, but now but you have to bounce back. Like I threw myself a little pity party for whatever, like a month, or I was like, wait, I got rejected. And then I read the comments and I was like, you know what? These are all valid. Like this paper wasn't very good. Like this paper was a little bit misguided. Like it didn't really, I get why it was rejected. And
Mhm,
so, using those moments to kind of like motivate you and be like, you know what? Yeah, I can do better. Like I need to, use this to catapult. But yeah, my my biggest, I would say, yeah, that paper specifically is one that's just like still kind of pinging in my head.
that's like
Um,
one of the worst things when you have a paper that you're just trying to publish and it's like old and you're like, I'm trying to do my new experiments and I
yeah.
still have to revise this old paper and it's like, kind of just, yeah, that can be totally, I totally understand where you're coming from with that.
Yeah, yeah. So that for me has been oh my gosh, such a slog. And then one other thing that I want to say, Brandon, is that my first year of graduate school at UCLA was brutal.
Mm,
It was so hard. Like and I wasn't expecting it to be easy, but the classes that I was taking, I had like a thermodynamics class, I had a dynamics class, I had atmospheric chemistry, I had, like some like hard classes. And the funny thing, and it's not that undergrad was a cakewalk for me. Like I definitely worked really hard in undergrad and I did not have a 4.0. I had like a 3.3, 3.2, which isn't bad, but it's not perfect.
mm,
And in grad school that first year, I was like, I don't know if I can do this. Like, well, I knew I could do research, but I didn't know if I could pass the classes.
mhm,
'Cause they were so hard. But then my mom actually she had something really amazing to say, which really helped me out and kind of like got me to dust myself off. She was like, Paige, like, this is the hardest level of school. Like, school doesn't get harder. Like, classes don't get harder
mhm,
than graduate courses.
mhm,
So they should be hard. They
mhm,
should be really hard. And if they aren't, then like something's wrong. Either the classes aren't hard enough or you were already mastered the material.
mhm.
So that's another point too, I think, where I was like, I don't know if I can do this. And then, she said that and I was like, good point, mom.
Yeah, that is cool.
You're right.
I was also team not low GPA, but not like stellarly high. I was also like a 3.2. Uh, and
Right.
so kind of touching off, what we talked about just previously for advice for young scientists, this
Hmm.
idea and what you just said about papers getting rejected and dealing with rejection. I went to a lot of labs, I remember, and approached a lot of labs trying to get that research position to get that experience. And a lot of people turned me away. They're like, your GPA is too low. It's not going to work out, man.
Yeah.
And if they could only, they only knew that I also like was working full time and stuff like that, and I was actually just like immensely passionate, and I just wanted to do work for them, I think I could have done great. But you just have to deal with that rejection, not get discouraged, and
Mhm.
keep asking professors, keep trying to get those connections going, because eventually, if you're passionate about something and you work really hard at it, good things are going to come your way. So yeah, just
Totally.
persevering, and like persevering through rejection and the failures of science is so important. So that's
It
why I want to ask
so
those failure
is.
questions.
Of course.
One thing I kind of want to close out with, which is like a beautiful quote from your newsletter, that I
Mhm.
just really liked. It resonated with me. You say your job is to be curious about something that you love. Can you give me a
Mhm.
little insight into what you meant by that and like your thoughts on that?
Yeah, yeah. I mean, at the end of the day, like, I am so profoundly lucky that my primary purpose right now is to look at the ocean and use tools to understand why the ocean is functioning the way that it is and why we're seeing patterns in certain areas and to even see the patterns. And it is such a gift to be able to, you know, sit and just think about something that I've always loved so much. And, sometimes I get separated from that because I get bogged down in, oh, like I'm so bad at programming. I'm so tired. Like, I have all these meetings to go to, I don't think this thing is working. But at the end of the day, like, what is it that I have to do? I have to get curious. You can't be a good scientist without being curious. You can like exist by going like A, B, C, D and following steps, but um I have to get curious to like actually figure out new things. And that's I mean, how many people get to say that, right?
Hmm.
That like
Hmm.
their job, that their day to day, that they just get to like let their brain just go wild.
Hmm.
Like think about all the possibilities and yeah, just let go and know that like you can go in any direction to a certain degree is like yeah, so it's such a gift and something that like I am thankful for. I try to be thankful for every single day. I will say that I have days where I forget that and I lose
Hmm.
sight of that and I'm just like bogged down and like just I'm grinding and I forget that like oh yeah, like every once in a while my advisor's like just like, look at the figures you're making. Like,
Hmm.
I make figures and I'm so focused on delivering things. Sometimes I lose sight of the fact that what's the real point is just to get curious. And so, yeah, that's just something that I've just been so thankful for, especially the last like 3, 4 years.
Hmm. Well, I think that's a wonderful sentiment and a wonderful attitude to have.
Thank
Thank
you.
you so much for being on the show. It was a terrific. I'm thankful to have had this experience and had you on the show.
This is so fun.
Is there anything that you want to say to maybe anybody in the audience before we wrap up here?
That's a great question. I don't know. I think and this goes beyond science, but I would just say life is too short. Life is way too short. You got to get curious. You got to find those opportunities. Everything we said applies in a scientific context, but it also applies in a greater context as well.
Hmm.
And I think, as you progress in life, if there's something that like sparks your passion, gets your enthusiasm, like you just gotta go and you just gotta pursue it relentlessly. Like, get comfortable with just going for it every day. And whatever that thing is, you will eventually, you might not feel like you belong, but you'll feel like you can do it.
Hmm.
Right. And I've
Hmm.
and I've been so lucky to have that experience in science. And, I'm lucky that science is like a marketable skill
Hmm.
that I can like make a living off of.
Right.
But, I still think that everyone should find whatever that is in their life, whether it's science, whether it's art, whether it's exercise, whether, it's anything, just find that thing and, yeah, just go for it relentlessly.
All right. Well, terrific advice. Again, thank you so much for being on the show. It was a pleasure.
Yeah, of course. Thank you.
If you like this episode, please be sure to like and subscribe to the channel. It would really mean a lot as I continue to grow the podcast and bring the latest and greatest science to all of you. And if you're particularly interested in this episode or oceanography and climate change and you want to learn more, I encourage you to visit Paige's newsletter, which is a wonderful repository of information where she has details regarding the cruise, essentially like a diary of her cruise, a weekly newsletter detailing her experience on this research vessel, the Thomas Thompson. And then, furthermore, on that website, you can also find her lecture series on climate change, entitled "Climate Change for Cool Kids During COVID." This is also a wonderful resource for anybody interested in climate science because it really breaks down all the intense science in a very easily understandable way that any non-scientist can readily understand. So if you want to find Paige's newsletter and learn a little bit more about this field, you can find that at https://paigehoel.com/scientist-page. And we'll have the link for this in the description for the video as well. Furthermore, if you're interested in actually getting involved on one of these Go Ship research vessels yourself, right? If you want to actually go on a research vessel and do this, research expedition, you can visit https://www.go-ship.org. Here you can find people to correspond with, and you can inquire about potentially getting on one of these research expeditions. So if you think oceanography is interesting and if this is up your alley, I highly encourage you to check this out. Thank you so much again for listening. Till next time, this is Goggles Off.